caresses it in search of a jewel that may be hidden inside. And that's what happens with this newfound link between accelerated motion and gravity. Einstein's mind returns again and again to images of people falling from roofs, rooms accelerating in empty space, or falling down toward the earth. And in the process, he realizes something profound. Imagine that I am in one of those rooms freely falling toward the earth. And as I'm floating around inside, I click on a laser. What will I see? Well, this is not a trick question. I'll see the laser light go straight across the room and hit a corresponding point on the opposite wall, that red dot over there. But what will you all see watching this from the surface of the earth? Well, you will surely agree that the light begins at the laser and ends at that red dot. But because from your perspective, gravity is causing the room to accelerate downward, you will see the light go in a curved trajectory. After all, that is the only way that the light can begin at the laser and end at the red dot, given that from your perspective, the room is falling ever more quickly while the light is in transit. What's the conclusion? In a gravitational field, light falls. As light sweeps along the contours of space imbued with gravity, it traces out curved trajectories, a direct link between gravity and curvature. And with this vital insight, Einstein can begin to see the glimmers of a new understanding of gravity taking shape. The idea is that if there's no matter, no gravity, then space is not curved. But if we bring in a massive body like the sun, then the environment, it responds. The environment warps. The environment curves in response to the presence of the sun, in response to the motion of the sun. And if we were to take a two-dimensional slice through this environment, we see that the Earth itself is kept in orbit because it's rolling along a valley in a curved environment that the sun creates. This is Einstein's proposal for how gravity works. Warps and curves in the fabric of space and time. And it's not a proposal that's meant to only work out there in outer space. It's meant to work everywhere, even here. As a body moves along, the environment, even here, it responds. It ripples. It curves in response to the motion of that body, in response to the presence of that body. And it's an idea that also applies to me, right? Now look, I am not a particularly big dude. So the curvature I'm creating is too tiny for you to feel. But according to Einstein, it is here to be sure, as this is the essence of Einstein's proposal. And what a beautiful proposal it is. You and I, the Earth, the moon, the sun, we are all surfing along the warps and curves in space and time, sliding along its chutes and valleys. Yet, however striking the idea, Einstein realized that there is still a monumental challenge ahead. He needs to marry mathematical might to this spectacular imagery. He needed to come up with equations that will predict the precise shape and amount of curvature in response to any given amount of matter or energy in space. But even so, even with the daunting challenges ahead, for the very first time in his life, Albert Einstein can feel that he is touching the fingertips of nature's hidden hand. Between 1908 and 1911, Einstein writes a couple dozen papers in physics, but none of them on gravity. Instead, he is focused on the early developments of quantum theory, while also wandering the academic world, from an initial post in Zurich to a follow-on post in Prague, and finally in 1912 back to Zurich. Now, during all this meandering, Einstein continues thinking about gravity, but it's his move back to Zurich that marks the turning of his full attention to the problem of gravity, figuring out how gravity works. And more established scientists who've been kind of keeping tabs on Einstein's preoccupations, they considered this focus on gravity to be foolhardy.
As an older friend, I must advise you against it. For in the first place, you will not succeed. And even if you do succeed, no one will believe you.
Einstein, surprise, ignores all the advice, and his famed Zurich notebook allows us to peer directly over his shoulder as he launches a full-throttle attack on gravity. First few pages of the notebook, Einstein is just summarizing known physics in the new language of space and time brought forward by special relativity, and nothing new here, just old ideas in a new formalism. But then we come to page 14. And like a bolt from the blue, Einstein begins this page with a simple, modest-looking formula that heralds one of the most dramatic of all scientific upheavals. The formula, it's a generalization of the Pythagorean theorem that we all learned in junior high school. Remember how that goes? You have a nice triangle like this, then a squared plus b squared equals c squared. Thank you. But if this triangle is warped, if it's curved, you can imagine that a squared plus b squared will no longer equal c squared. Instead, when it's curved, you need a new formula. And that's what the formula on the top of page 14 provides. Einstein's own little doodling in the margins lets us see what pushed him in this direction. Grossman, Marcel Grossman, yeah, the very same kid whose class notes helped Einstein to graduate. The same kid whose father finagled a job for Einstein at the patent office. That kid is now a professor of mathematics at the Zurich Polytechnic. So when Einstein returns to Zurich, he decides to drop in on his old friend for a little casual advice on how to describe curvature mathematically.
Grossman, you must help me, or I shall go crazy.
Grossman obliged.
I looked over the literature and soon discovered that the mathematical problem was already solved. The entire development followed the Gaussian theory of curved surfaces, which was the first systematical use of generalized coordinates. Riemann's achievement was the biggest. He showed how one can form a field of tensors, GIK, of the second differentiation rank.
Marcel Grossman, ladies and gentlemen. But yes, that mathematical gibberish really does mean something, something important. Grossman had found that the math for describing curvature had already been worked out in the 1800s, which would mean Einstein would not have to start from scratch. But the papers themselves, they gave Grossman pause. The equations were dense and cumbersome.
It is a terrible mess. Physicists should not be involved with it.
Which only encourages Einstein to dive right in. And he quickly concludes that the situation is actually stunningly fortuitous. Sitting on the dusty shelves of the library is the mathematical architecture that might very well allow him to construct his generalized version of relativity. To top it off, Einstein would not have to go it alone. He had his old friend Marcel Grossman to guide him through the mathematical thicket.
I'm now occupied exclusively with the gravitational problem and believe I can overcome all difficulties with the help of a local mathematician friend. But one thing is certain. Never before in my life have I tormented myself anything like this. And that I have gained great respect for mathematics, whose more subtle parts I'd considered in my ignorance until now as pure luxury. Compared with this problem, the special theory of relativity is mere child's play. Whew.
In the Zurich notebook, we see Einstein immersing himself in that mathematics. He's trying out the notation over here. He's doing rudimentary calculations over there. Now, today, all this material is standard. I teach this to undergrads. But in 1912, all of this material was foreign. But even so, Einstein quickly gets the hang of it, allowing him to push forward on two parallel tracks. First, Einstein uses the mathematics to guide him toward equations that will be general, in the sense that they will work equally well whether you're sitting still or falling from a roof. Remember, that is the general of general relativity.